Okay. Good morning, students. Today's class we will discuss about phase transformation of pure substance and quality of steam. What is pure substance? The chemical composition of the substance is not changing with the phase. It may be solid, it may be liquid, it may be vapor. The chemical composition is not changing. It is invariable chemical composition in all phases, then it is called pure substance. In the universe, God gifted pure substance is what? What is the importance of pure substance? Suppose, consider for the power plants, the boiler, liquid to vapor phase, turbine, vapor, high pressure vapor to low pressure vapor, and some wet steam condition it is coming. Maybe the drainage fraction will reach up to 0.7, means some moisture content of the steam is coming. In condenser, that moisture steam is condensed to the liquid. So different phases is there. How we can decide the material? Every time chemical composition is changing, it will damage it will reduce the life of the plant, individual components. So the pure substance is required as a working medium, especially in power generation. The God gifted pure substance is at present freely available is water. The second advantage of this water, having high latent heat of vaporization, means 1 kg of steam is capable to, at 1 atmosphere pressure, is capable to carry 2250 kilojoules per kg of heat. At present, no fluid is available that much of high heat carrying capacity. That is second advantage. One is if the chemical composition is not changing. That's why in this unit purely we will discuss about the properties of steam directly. The phase transformation of the steam, suppose from minus 20 degrees to 100 degrees, above 100 means 110 degrees or 120 degrees, means ice, solid ice to the superheated steam. How many phase transformations are there? Minus 20 degrees to 0 degrees ice first. This is a solid heat, sensible heat rejection. Then after 0 degrees ice to 0 degrees water, latent heat of fusion. Here temperature is constant. There is no change of temperature, but heat transformation is there. Next, again the heat absorption 0 degrees to 100 degrees of water. It will absorb the heat, sensible heat. The specificity is 4.2, ice specificity is 2.1 kilojoules per kg Kelvin. Next, 100 degrees water to 100 degrees steam, latent heat of vaporization. Here also temperature is not changing, but heat addition is taking place. Phase change is coming to the picture. Then after, sensible that saturated steam to the superheated. This is the phase transformation of the pure substance. Sensible and latent heat, representation by temperature and heat curve or pressure and volume curve, pressure and temperature curve, whatever it may be. This is the vapor saturation curve. This is called, in TS diagram already we introduced in last subject, in entropy subject. This is called saturation curve. Means this side saturation curve, it is called liquid saturation. This side is called vapor saturation. For water, this is the saturation curve under TS diagram. So upon the saturation curve, the saturated liquid or saturated vapor, directly we can extract the properties from the steam tables. So table number 1 and table, saturated liquid and saturated vapor. And whatever the phase transformations we discussed, solid ice to superheated steam, that is not required for our power generation. Subcooled liquid to superheated steam is more than sufficient for our power generation cycle. So we restricted Total phase transformation we are not considering for our study properties of steam. Here only subcooled liquid to superheated steam. These are the conditions you can see. At state A, this is the, I already mentioned. Upon the saturation curve, this is the saturation liquid. Less than that, saturation subcooled liquid. So less than the saturation liquid properties. Next to at point B, saturation liquid. This is wet region. With this wet region, how we are describing is based on the dryness fraction. If dryness fraction x, we are denoted by, I will show the equation. Dryness fraction x, mass of vapor by mass of vapor plus mass of liquid. This is the dryness fraction. 100% dry means it will come to saturated vapor. Means mass of vapor by mass of vapor. There is no mass of liquid. Or 100% liquid, mass of vapor is 0, 0 by something is 0. So it is a saturated liquid. So X value is varying from 0 to 1. 0 means saturation liquid, 1 means saturated vapor, in between means wet region. But these three stages, saturation liquid or saturation vapor or this wet region, the temperature is constant. There is no change in temperature. This is the first condition. Next, after saturation vapor, further heat addition is taking place. Superheated steam. This is the E. So, saturated vapor properties plus some sensible heat is there. So, these are the stages. Subcooled region, saturated liquid, wet region, saturated vapor and superheated. Saturated liquid, saturated vapor and superheated region, from the steam tables directly we can extract the properties majority. Table number 2, pressure based saturation liquid saturation vapor properties. Table number 3, superheated specific volume. Table number 4, specific enthalpy. Table number 5, specific entropy. But this wet region and subcooled region we want to calculate. And superheated region also, round figures are there, we can extract properties from the table. Otherwise we have to calculate. How we are calculating, we will discuss now only. So property evolution. At saturation levels, directly we are extracting tables. Next, wet region. At X dryness fraction, suppose enthalpy I want to extract. At X dryness fraction, HF saturation liquid enthalpy plus X into Hg minus HF. That is only total. If X is equal to 1, there is no issue. We can directly add total latent heat of vaporization. But if dryness fraction is not 1, then 0.8 or 0.9 into dryness fraction. So wet region properties, how we are extracting is, for enthalpy, suppose example, Hx equal to Hf plus X into Hg minus Hf. Like entropy also, Sf plus X into Sg minus Sf. Like internal energy also, once you know the enthalpy, enthalpy equal to internal energy plus flow work. So you subtract enthalpy minus flow work, you will get the internal energy. Directly from steam tables you will not get the internal energy. Internal energy is same, and specific volume also same. Vx equal to Vf plus X into Vg minus Vf. This is so at wet region we are extracting properties like this. Next, at superheated region. At superheated region, suppose H superheat is there. Hg up to saturation vapor, what is the enthalpy we are extracting from the table number 2, plus remaining sensible heat Cp into specific heat of the steam, they will give you a problem. T superheat minus T saturation. If these temperatures are round figures 350 degrees, 250 degrees, 400 degrees, means from the steam table, table number 4, directly you can extract the property. Otherwise you have to calculate specific heat of the steam continuously changing with respect to pressure and temperature. So they will in the problem they will provide the value. In general case, the specific heat value is varying from 2.1 to 2.6 kilojoules per kg. Next, S superheat also. S superheat is equal to Sg plus remaining sensible heat entropy change Cp into Ln T superheat by T saturation. But coming to the specific volume, according to Charles' law, V superheated by T superheat equal to V saturation by T saturation. Gases volume by temperature is constant. So V superheated by T superheat equal to V saturation by T saturation. So V saturation from the particular pressure, T saturation pressure temperature, it is coming directly from the steam table. T superheat temperature you will provide in the problem, then calculate the V superheat value. So this is the method for calculation of the superheated region. Next, subcooled, same HF minus Cp into HF is there less than enthalpy of fluid. So minus how much less than the sensible heat subtraction. Cp into T saturation minus T subcooled. Next, S also, so entropy also, S subcooled is equal to SF minus Cp into Ln T saturation by T subcooled. But specific volume, subcooled and saturation liquid, specific volume is not changing. Already saturated liquid specific volume itself 0.0001. Even though it is moving subcooled region, the change is negligible. Directly we can consider the specific volume of subcooled equal to specific volume of saturated liquid. So this is the methods how we can extract the properties. Next, one more method is a Moiler diagram. All are knows. The basic in flow process for determination of the available energy, continuously two properties are required. One is enthalpy, second one is entropy. So Moiler is developed relation between enthalpy and entropy. The enthalpy in x-axis, entropy in y-axis. Sorry, enthalpy in y-axis and entropy in x-axis is represented. This is called saturation curve. Same similar lines are following by the saturation curve is the drainage fraction lines. X value, drainage fraction 0.9, 0.95, 0.9, 0.85, 0.8, 0.75 and zero point 0.7. Different drainage fraction lines. These are the pressure lines. 0.01 bar to some it is shown 500 bar also, but max 100 bar general Moiler diagrams are available up to 100 bar. These are the pressure lines. Below the saturation line, pressure lines and temperature lines are equal. After saturation curve, the temperature lines are deviating. You see 50 degrees, 100 degrees, 120, 300, 400. So now the pressure and temperature given means we can extract enthalpy and entropy. Suppose 400 degrees centigrade and 20 bar pressure. You see, this is the 400 degrees temperature and this is the 20 bar line where it is intersecting. This is the point. So what is the enthalpy? 3200 something, 250. What is the entropy? 7.2 kilojoules per kg Kelvin. So directly we can extract at any condition the enthalpy entropy values. It is superheated condition, saturation conditions, irrespective of calculation of the properties. Moiler diagram, especially we are using throttling process. That one I will discuss in next class. This is the just how we are extracting the properties and representation of the Moiler diagram. Thank you. Thank you very much.